Hi, I'm Vishesh, and I'm going to be going over Physics 2 Lab 4. So the overview for this lab. The purpose of this lab was to use ammeters and voltmeters to predict and experimentally determine the behavior of conventional currents and potential differences in circuits. We also wanted to use the loop rule and the node rule to observe the behavior of resistors and capacitors in these circuits as well. Some important themes for this lab were energy conservation, the loop rule, which involves potential differences, the node rule, which involves conventional currents, and the change in voltage for a round trip, and how capacitors function in circuits. So, procedures for the part 1 of this lab. We first wanted to predict the current for a series circuit using V equals IR, which you can see on the top left. Our V was 3 volts from the 2 batteries, and our REQ was 147 ohms from the 2 resistors. We predicted there should be a current of 0.02 amps. We then set up a series circuit and found that this same current value was measured when the ammeter was inserted. If you put in an ammeter backwards though, you'd get I equals negative 0.02 amps because the current is being read backwards on the ammeter. Next, we wanted to measure the potential difference where an ammeter was. So we took out an ammeter and put in a voltmeter. And we found that the delta V is equal to 3 volts. And this is because the black wire end is connected to where the batteries are, so there's going to be a potential of 3 volts. The red wire was connected to the red one was connected to a wire which had 0 volts because the circuit was broken. But the remaining ammeter read I equals 0 amps because no current was flowing since the circuit was left open and not closed. So then we wanted to find the voltage differences and graph these. So we found the potential differences across different points on the circuit, which you can see on the bottom right-hand screen. And we can see that between A and B, we had a negative 3 volts difference. Between C and D, there was 0.959 volts difference. And this is because this was between the resistors with 47 ohms. And then you had between E and F with 2.041 volts difference. And this is between the bigger resistor, the 100 ohm resistor. And if you sum up all these delta V's, you get 0 volts for a round trip. And it's important to note that the addition of the voltmeter did not affect the current because it has infinite resistance in this lab simulation, so no current flows through this route, even though technically it's in parallel. So then when we add the ammeter in parallel, we can see that the ammeter is going to be in parallel with the 100 ohm resistor, and the current on both ammeters is going to be different. It's going to read 0.06 amps instead of 0.02 because of the node rule. The current is split between the ammeter and the 100 ohm resistor, which is in parallel with it. And since the 100 ohm resistor is going to be resisting on that route, and our ammeter has no resistance in the simulation, because of the node rule, our current is going to all try to go through that zero resistance path through the ammeter, and therefore only the 47 ohm resistor is really being used in this lab. So both of the ammeters are going to read the same current of 0.06 amps. And this means that the only resistance this current encounters is going to be the 47 ohm resistor. So when we wanted to calculate the actual resistances, we could use the delta V values that we found across the different ohm resistors and across different parts of the wire, and we could use I current, which is the same for all the different components, and we could find that the R of the 47 ohm resistor was actually 47.95 ohms, and the resistance of the 100 ohm resistor was actually 102.05 ohms. But the R of the wire is going to be 0 ohms because there's 0 volts potential difference, and the R of the ammeter is also going to be 0 volts because, like we discussed, there's no resistance in the ammeter for the simulation. So then we wanted to observe charging a capacitor. So when we charge one, the light bulb first starts off really bright and the current flows at maximum capacity. As time is bigger than 0, the capacitor is charging and the bulb starts to dim and the current slows down. As time passes a lot more than 0, the capacitor is fully charged and the bulb is off and the current has stopped flowing completely. When we want to discharge a capacitor, the light bulb starts off bright again and the current flows at maximum capacity. As time is bigger than 0, the capacitor starts discharging, so the bulb dims and the current slows down. And as time has passed a lot more, the capacitor is fully discharged, so the bulb is off and the current stops flowing. Important to note, though, that when you discharge a capacitor, the current is going to be going the opposite direction and is reversed compared to when you charge a capacitor. So then when we did an experiment with charging and discharging this RC circuit, we could find some values. So when we looked at the 10 ohm bulb, the time it took to charge the capacitor was 10.13 seconds. The time to discharge was 13.98 seconds. And you can see that the values for the 20 ohm bulb were slightly different, but almost double of the values of the 10 ohm bulb. And this is because we could expect that if we double the resistance, it's going to be double the time for the capacitor to charge and discharge. So then we wanted to graph our discharging capacitor time dependence on voltage. So on this right-hand side of the screen, you can see that we have our time values from 0 to 20 seconds, and we have our instantaneous voltage delta V values in the middle column. And then you have ln of V over V sub naught, which is going to be us linearizing our data so that we can plot it on this middle graph, which has our ln of V over V naught versus time graph. And so this line of best fit that we get is going to be important on this next slide because we can compare it to this linearized form of the equation, delta V equals delta V sub O e to the negative t over RC, and we find that our slope that we find is going to be equal to the negative 1 over RC. So then we can use that to find our RC value, which is equal to 6.906 seconds, which is close to our RC value in the circuit simulation, which is 6 seconds. So then we had some extra questions for the lab. If we did this lab in real life, the real ammeter would have some small resistance, so the overall current reading in the circuit would be smaller than just the ideal value we predicted. Another question we had was if we had to do this model in real life again with just a battery and a capacitor, what would be different? So in this lab model, in the simulation, if we had a battery and a capacitor, the capacitor charges immediately upon connection. However, in real life, all circuit components have some sort of resistance, so this would still take some time, even if there's just a battery and just a capacitor, to fully charge a capacitor.